viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani, Associate Professor, Department of Computer Science, Aryabat College, University of Delhi. So in our previous lectures, we looked into the union find data structures and one of their prominent applications, which is Kruskal's algorithm to find minimum spanning tree. Moving on to the next topic in this lecture series, which is about randomized quicksort. But before going into randomized quicksort, we need to understand that what actually quicksort is and what is going to be the difference in this kind of randomized quicksort and quicksort. So first we'll take a complete look at the quicksort algorithm. We'll try to understand that, and then we'll be moving on to the next version, which is kind of randomized quicksort. So coming into quicksort, as the name indicates, it's a sorting algorithm, and this quicksort is based on divide and conquer technique. So what kind of divide and conquer technique this quicksort is going to imply is it picks an element as pivot and partition the given array around that picked pivot. So after partition, we have pivot at its position or pivot at some position, and to the left of the pivot it is having all the elements which are less than the pivot in the first pass, obviously not in the sorted order, but to the left all the elements which are less than pivot, to the right of the pivot all the elements which are greater than pivot. Now this choice of pivot is very important in case of quicksort, and this choice of pivot is a factor which is going to create a line of difference between quicksort and a randomized quicksort, because the way in which quicksort picks the pivot and the way in which randomized quicksort picks the pivot, these are the two kind of different techniques. So choices of pivot, if we talk about, it could be any random element, it could be first element of the array, it could be last element of the array, or it could be median of the array. So this choice of pivot is obviously very crucial one, and each and every choice is having its own effects on the whole functionality of this quicksort. Now the key step, if we talk about, so take any kind of divide and conquer algorithm. So generally this divide and conquer algorithm are implemented in the natural way, which is using the recursion. So binary search, if you can say, this binary search is also a divide and conquer algorithm, although there is an iterative way of implementing binary search, but more natural way is kind of implementing that using recursion. Similarly, if we talk about merge sort is also a kind of divide and conquer problem, or based on divide and conquer technique. So divide and conquer technique, again we generally prefer to call merge sort through recursion, or to implement merge sort through recursion. So we are going to do this recursive solution here also, because recursive solution are kind of more natural way of calling any technique or any solutions, if we can say. So when we look into various steps of quicksort, the major key step here is we can say the function partition. The task of this function partition is to put pivot at its correct position in the array, put all the smaller elements before the pivot, which is on the left side of the pivot, put all the greater elements which are greater than that pivot after that pivot, and the whole process is going to take linear time. Yes, the whole process is going to take linear time. So that's what the beauty of the algorithm is. So we will be taking a pivot in the first iteration. This pivot will take its kind of, we can say, correct position in the sorted array. So, whatever the position in the sorted array is, that will be taken. All the elements which are less than the pivot will be kept on the left side of the pivot. All the elements which are we can say greater than the pivot will be kept on the right side. This is what the key step of this quick sort is, and this key step is known as the term is given the term partition. So, we are going to find a pivot item in the array. This item is the basis for comparison for a single round, because every time your pivot is going to be changed, and for this we in order to move further, we will start a pointer which is we can say is left pointer at the first item in the array, and start a pointer which is a right pointer at the last item in the array. We keep on moving these two pointers. Left pointer will go in the right direction, right pointer will go in the left direction. But when? While the value at the left pointer in the array is less than the pivot value, move the left pointer to the right. That means the value at the left pointer, when it is less than the pivot value, that means it is in the correct, it is on the correct side. So, no need to shuffle that value, no need to swap that value, we will just move the left pointer to the right. We will be taking an example, we will be taking a visual example of this, and this will continue until the value at the left point is greater than or equals to pivot value. So, whenever after moving this left pointer we encounter a value which is greater than or equals to pivot value, that means this value is not in the correct, not on the correct side or not in the correct partition, and we stop here, we stop moving our left pointer at this point. While the value at the right pointer in the array is greater than the pivot, move the right pointer to the left. So, start kind of we can say shrinking the array in a way. So, we have moved left pointer to the right direction, right pointer to the left direction, because we want I have talked about recursion, we want a base condition also. So, base condition is going to be when this left and right pointers are going to we can say cross each other. So, after that you need to unwind the recursion. So, we will while the value at the right pointer in the array is greater than the pivot value, we will be moving the right pointer to the left direction and continue until the value at the right pointer is less than or equals to the pivot value. Now, we have a left pointer on the value which is greater than pivot, we have a right pointer on the value which is less than pivot. That means we need to swap these values in order to make the partitions in the correct way. So, if the left pointer is less than or equals to the right pointer, then swap the value at these locations in the array. Now, move the left pointer to the right direction by 1 and right pointer to the left direction by 1. And if this left pointer and right pointer do not meet, then repeat the process. So, that means you will keep on repeating the process, moving left pointer towards the right till we have smaller values smaller than pivot, moving right pointer to the left till we have values greater than the pivot, and when these two pointers are going to cross, we will stop repeating the process. So, if till this left pointer and right pointer are not meeting, we need to repeat the process. So, here if you can see on the screen, first of all we have determined the pivot. Let us say we have taken the pivot as 5. So, left pointer if you can see is on 4 and the right pointer is on 9. Both are fine. That means 9 is a value which is in the right partition greater than 5, perfectly okay. 4 is a value which is in the left partition less than pivot, that is also fine. So, we will move the pointer. So, we have moved we have shifted the left pointer, value is 2, again we have shifted the left pointer, now value is 6. Now please understand that value 6 is something which is not in the correct partition if I am talking about. So correct partition, that means the left partition must have all the values which are less than your pivot, which is 5 presently, and we will stop our left pointer here. Then we focus on the right pointer, start moving that right pointer towards left. The first value after 9, obviously the first value is 3. So now 3 is again we can say in a wrong side, is on the wrong side or in a wrong partition. That means 3, the value which is less than pivot, should be on the left side, and 6, the value which is presently on the left side, must have been the proper place for this is the right partition. So by moving both the pointers one by one, we have arrived at those two values which are in the which are misfit in their partitions. So we are going to swap these two values. So 3 has taken the place of 6, 6 has taken the place of 3. And now moving further, if you can see the step 7 here, if you can see this step 7 here, now our left pointer has moved one position and came to the pivot position. Similarly with the right pointer has also shifted one step towards the left, and it has now both the pointers are at the we can say both the pointers have met. So we will stop repeating this process. Now please see that on the left side of the pivot we have 4, 2, 3 which are the elements which are less than the pivot, and on the right side of the pivot, if you can see, we have elements 6 and 9 which are the elements which are more than the pivot. So now we are going to do this process repeatedly by doing the same step for the left partition as well as for the right partition. So this is what kind of, that means now we will be calling this function recursively. So here we have understood the kind of we can say one iteration of the quick sort, in which we have seen now that pivot is at its correct position, the left side of the array, the left partition, although not sorted but having all the elements less than 5, the right partition again although not sorted, here in place of only 2 elements which are 6 and 9, it seems sorted, but it could have been 9 and 6 also. So that is something which we need to take care of. So right partition obviously having 2 elements which are they could be in non-sorted manner, but one thing is very sure, that right side is having right partition is having all the elements greater than pivot, and left side is having all the elements less than pivot. What does this indicate? This indicates that your pivot, which is 5, is at its correct position. So 4, 3, 2, we can shuffle them, we can arrange them, ultimately it will be 2, 3, 4 after calling this function recursively for the left partition, we will be able to arrange it, and after calling this function for the right partition, we will also be able to arrange this 6 and 9 would have been 9 and 6 also. So here we have seen that after first iteration, the pivot element has taken its own place. Now one thing here is one more example, if you can see on the screen. So the array here is 1, 7, 6, 8, 0, 9 and 2. So we will be choosing one pivot, and so here my pivot is 2, that means I have chosen the left kind of the rightmost element as the pivot. That could also be one idea, or I can choose the leftmost element which is 1 here as the pivot, or I can choose any random element as the pivot, or I can choose kind of, we can say, median of all the elements as the pivot. So, here if I am going to choose 2 as pivot, I will be moving my left pointer from starting from 1. So, 1 which is less than 2 is in the correct side. I am moving the pointer to 7. Now, 7 is something which is obviously should not be on the left side of 2. 2 will take its own place. Here if I am talking about so we will stop this left pointer here. Taking from the right side, we have started with, let us say, 2, 2 is our pivot, 9, 9 should be on the right side, that is on the correct partition. Next comes 0. Now, 0 is something which should be on the left side of the 2, when 2 is going to take its own place. So, now the left pointer at 7, the right pointer at 0, we have found 2 candidates which are to be swapped. So, we have swapped 0 and 7, as you can see in the third step. Now, the left pointer is moved to 6 and then so on and so forth. So, this step we are going to repeat, and at the last step, if you can see the array, it is 1 0 2 8 7 9 6. So, this indicates that the element 2, which is pivot, is at its right position, 1 and 0, unsorted array, all elements less than pivot on the left side, 8 7 9 6, all elements greater than pivot on the right side, obviously in the unsorted form. And then we will be calling this function recursively for the left side as well as for the right side also. So, this is what your kind of strategy is when we say quick sort. If we look into quick sort, as I have told you that this is going to be a recursive function, let us try to see the code in a quick manner. So, we have a function quick sort in which we have given A is nothing but the input array, then we have given P and R. So, P is the left limit, R is the kind of right pointer, I can say. So, if P is less than R, so this is the condition which is kind of, we can say, is going to be the base condition when your recursion will start unwinding. Q is going to be the pivot element. So, Q is the partition of A comma P comma R. So, when you are going to call this partition, this will result in an element Q or at a position Q, and from P to Q it is going to be the left partition, and from Q plus 1 to R it is going to be the right partition. So, we have called quick sort for the left side as well as we have called the quick sort for the right side also. What is remaining here is the partition procedure, and here is the partition procedure in which we have taken the last element as the pivot, and then we keep on moving the pointers which are the left pointer as well as the right pointer, and then we swapped as and when required. So, this is what your partition function is, which is being called inside the quick sort, and then quick sort is being given kind of we can say recursive calls to this. Now, if we talk about quick sort particularly, it is very useful for sorting the arrays, but in efficient implementations our quick sort is not a stable sort. When we talk about the stable sort, that means relative ordering of the equal elements should be preserved in the output array. That is what we call stable sort. But in efficient implementations, when we talk about quick sort, it is not a stable sort, meaning that the relative order of equal sorting elements or the same sorting elements is not preserved actually. So, this is what the problem with the quick sort is. So, that wherever stable sorting is required, you cannot use this quicksort, otherwise the time complexity wise it is going to give you a decent time complexity, in the sense the overall time complexity of the quicksort is n log n, but in the worst case it makes order n square comparison. But the best part with this quicksort is this behavior is rare, this worst case behavior is rare. Space complexity obviously it is an in place sort, does not require any extra storage kind of thing. There can be n log n for the average case, the complexity is order n log n for the best case, and the worst case it is going to make order n square comparison. So, here if you can see, I have given you 2 trees which are giving the picture of worst case in quicksort as well as the best case in quicksort. So, when we say the best case, that means the partition is almost half, or it is dividing into equal partitions. So, n is n by 2 elements on the left and n by 2 minus 1, I can say to be precise, on the right, because 1 is a pivot. Then same, that n by 2 is again going to get divided into n by 4 and n by 4. Worst case tree or worst case partition, if you can see, that is kind of an skewed partition. So, that says n minus 1 partition, n minus 1 elements one side and 0 element on the another side. Then we have for this n minus 1, we have 0 element on one side, take the pivot on pick the pivot separately, n minus 2 on the next side. So, this kind of an skewed we can say worst case is going to give us or this kind of an skewed tree. So, is the situation where you can say your partition or your pivot element is either the smallest element or the largest element. So, whatever element you are going to pick, if it is the smallest element, then the left partition is empty. If it is the largest element, then your right partition will remain empty. So, this is the worst case of the quicksort. As far as best case is concerned, we can say almost equal number of we can say elements in both the partition will give you the best case. Now, when this worst case is going to occur, this worst case, when I told you that no elements on one of the side, either the left side is empty or the right side is empty, this is going to happen generally when the array is already sorted either in increasing or in decreasing order. Now, why it is happening? This happens because the pivot becomes the largest or the smallest number each time respectively in increasing or decreasing order, and thus it will give one partition empty and all other elements in the next partition, and then it is going to kind of if you try to find out the complexity of the algorithm, it will give you a worst time complexity of theta n square, and this is what the case as I have depicted in this worst case in quicksort. Now, best case, if we talk about best case, is going to occur when your partition always occur kind of at the midpoint. So, the time complexity is going to be equals to the merge sort, which is given by the recurrence as T of n is equals to 2 into T of n by 2 plus theta n for this merging thing. So, the best complexity obviously comes to theta n log n. Then additional space, n log n additional space is required. It is not a stable sorting technique, as I have already told you. Now, this was everything about the quicksort, but what is going to take us to the randomized quicksort is the choice of pivot. So, when we choose pivot, there are some strategies. If we choose the leftmost or the rightmost element as the pivot, what are the pros and cons? This strategy is simple to code and pivot is always kind of fast to calculate. Either you are taking the leftmost element or the rightmost element. But please imagine if the data is sorted, or even if it is nearly sorted, this quick sort is going to give you the worst case skewed tree, because the elements are already sorted. You have taken the leftmost element as the pivot, all the elements on the right side of the partition, nothing on the left side, or vice versa in case of the rightmost element. If we choose the middle element, again it is simple to code, fast to calculate, but it is slightly slower than choosing leftmost or rightmost element. But this still can degrade to order of n square. So, we can easily construct an array that is going to give you order of n square in this kind of situation when you are picking middle element. What if a median of 3 is being chosen? Again we can say simple to code, reasonably fast to calculate also, but slightly slower than the above methods. But again chances of getting it degraded to order n square are still there. Fairly easy for anyone to construct an array that will cause it to degrade to order of n square. Now the last strategy which comes up here is choosing the pivot randomly. Choosing the pivot randomly by choosing the random function will take us to our next lecture, which is nothing but randomized quicksort. Although choosing the pivot randomly is also simple to code, but harder for someone to construct an array that will cause it to degrade to order n square, because every time you are picking an random element which no one knows that which element is going to be there. Although selecting a random pivot element is fairly slow, but yes, we can say sometimes it can degrade to order n square. So we can use any of these methods, and we will focus on choosing the pivot randomly, and we will be moving in our next lecture, we will be moving to the randomized quicksort. So till here we looked into the quicksort. We have seen dry run of quicksort. We tried to understood the strategy and the algorithm, and we have looked into what all choices of pivot can be there and what are the pros and cons associated with each and every choice of pivot. In the next lecture I will take you to the randomized quicksort. This is all from my side for this lecture. I hope you have enjoyed one. Thank you.